Okay, so hello and welcome back. So the last example that we have here related to this part is example number 6, and the question here is, let R be the relation defined in the set A. So you have some set A which is basically 1, 2, 3, 4, 5, 6 and 7. And you have some relation in this set R. The relation is all the ordered sets, all the ordered pairs A comma B, such that both A and B are either odd or even. And you want to show that R is an equivalence relation. Now to show that R is an equivalence relation, so you have to show that you need to show that R is symmetric reflexive and transitive. So now number 1, to show that R is, for example, reflexive, what you need to do is basically, so that the condition for being reflexive is that basically we say that for every A belonging to the set A, for example, then A comma A has to belong to R. This is the condition. Now this situation is basically something like this. So you have this set over here 1, 2, 3, 4, 5, 6 and 7, and R is basically some relation in this set that says that R is all the ordered pairs A comma B, such that both A and B are either odd or even. That means that once you form the Cartesian product of A and A, you will get some set here, and this set contains all of these elements, like for example 1 comma 1, 1 comma 2, 1 comma 3, 1 comma 4, and so on and so forth, all the way up to 7 comma 7. Now once you have this set, R would be a subset of basically the Cartesian product of A and A, which means that now the subset, how basically the way that you can decide which elements you can pick from here and put them together to call it R, basically is that basically A and B are supposed to be either odd. Both of them are supposed to be either odd or even, meaning that, for example, 1 comma 1, you could choose that. 1 comma 3, you could choose that. 7 comma 7, you could, but the rest of them you cannot. Or for example, if I write for example 2 comma 2, you could choose that. 2 comma 4, you could choose that. But for example 2 comma 3, you cannot choose that, because as you can see in this case, both of these numbers are odd. Both odd, both odd, both even, both. But this over here, one of them is even, one of them is odd, so you cannot choose that. So then based on that, you will get this set you will get this set R containing all such elements. Now, in order to decide whether R is reflexive or not, you want to know if for every A belonging to A, if A comma A belongs to R, right? So of course for every A belonging to A comma A can belong to R, because if A is any number, whether it's odd or even, then we are talking about A and itself. So if A is even, then again A is even, so based on this rule they fit together, and so they will be a part of R. If A happens to be odd, then if A happens to be odd, again, well, A is odd, right? So odd and odd will fit together, and that would be a part of R, and so you can use it. Which means that you can say that for every A belonging to the set A here, of course you can simply write the same condition, because the set is already called actually I was using some other thing. Okay. The set is already called A, and I'm saying for every A belonging to A comma A belongs to R. And so that basically shows that R is reflexive, right? Now, number 2, to show that R is, for example, symmetric. Alright, so to show that R is symmetric, what you need to do is that the condition is that basically for every A and B belonging to the set A, basically if A comma B belonging to the set R has to imply that basically B comma A also belongs to the set R, which is the case because if A and B if A and B belongs to the set R, that means that both A and B are either odd or even. So if both A and B are either odd or even, and for the same reason they belong to the set R, then again both A and B are either odd or even, and so they belong to the set R. So this is already the case, which means that basically R is symmetric. Now number 3, to show that R is transitive, the condition for that is that for every A, B, and C belonging to the set A, A comma B belonging to the set R and B comma C belonging to the set R has to imply that A comma C also belongs to the set R, right? Now what that means is that if you have if A, B, and C, if the 3 of them belong to the set A, all of them belong to the set A, then if A comma B belong to the set R and B comma C also belongs to the set R, then that means that then that implies that A and C, A comma C belongs to the set R. So now suppose that for example two even numbers belong to the set R. So for example, over here we have 2 and 4. So 2 and 4 does belong to the set R because both of them are even. And 4 comma 6 also belongs to the set R. Now of course you know that 2 comma 6 does belong to the set R because both 2 and 6 are even. On the other hand, for example, suppose that 1 comma 3 belongs to the set R. Both are odd numbers. And suppose that 3 comma 5 also belongs to the set R. Both are odd numbers. So you know that basically 1 comma 5 does belong to the set R because again they are both odd numbers. So that is also basically the case already. That is also the case already, and so you can say that let me put this over here, and I'm at 1138. Okay. So that is so we said that is already also the case. I have to mess with this thing. Okay. So we said that is already also the case, and so that means that R is transitive. So we have shown that basically R is reflexive, symmetric, and transitive, and so you can say that basically R is what do you call it? An equivalence relation. Is an equivalence relation, right? So that is that. So now that we have shown that R is an equivalence relation, further we want to show that all elements of the subset 1, 3, 5, 7 are related to each other. And all elements of the subset 2, 4, 6 are related to each other, but no element of the subset 1, 3, 5, 7 is related to any element of the subset 2, 4, 6. So what we have over here, let's consider basically two subsets of this set. For example, call them A1 and which is for example 1, 3, 5, 7. 1, 3, 5, 7. And let's consider another subset of this set, A2, and let's say that is 2, 4, and 6. You can see that basically A1 intersection with A2 is equal to the null set, and also A1 intersection union with A2 is equal to the set A, right? And we argued before that basically as you can see A1, you can say that A1 is the set of all even numbers, A1 is the set of all odd numbers existing in A. Also, you can say that A2 is the set of all, there's some all over here, of all even numbers existing in A. Now, in the discussion that we had in the previous video, we said that we did say that basically if I take, for example, the example of A1 and A2, you can say that under the relation R, all the elements of A1 are related to one another. All the elements of A2 are related to one another. And no element of A1 is related to any of the elements of A2, because based on what we are saying here, we are saying that basically R is the order per se comma B, such that both A and B are either odd or even. So I cannot pick some element from here, some element from here, and put them together as an ordered pair, because one of them would be odd, one of them would be even. So which means that no element of A1 is related to any of the elements of A2. On the other hand, all the elements of A1 would be related to all the other elements of A1, basically, right? So I can say that basically for all A and B belonging to A1, then you can say that A comma B belongs to R. And you can also say that for all A and B belonging to A2, A comma B does belong to R, right? Meaning that all the elements of A1 are related to one another, all the elements of A2 are related to one another, and there is no element of A1 which is related to an element of A2, and vice versa. Meaning that you can say that for all A belonging to A1 and basically B belonging to, for example, A2, A comma B does not belong to R, and vice versa. Right, so we understand this thing now. And here we showed that basically the intersection of the two sets is the null set, and the union of the two sets is basically the set A. So basically now so you can now call this basically an equivalence class, and you can call this also an equivalence class, right? And also you can say that, and of course you know that R over here is an equivalence relation. R over here is actually an equivalence relation, right? So and if you remember, we said that basically in the previous video, we said that given an arbitrary equivalence class, given an arbitrary equivalence relation, I'm sorry, not an equivalence class, but an equivalence relation, relation R, for example, in an arbitrary set X, R divides X into mutually disjoint sets. R divides X into mutually disjoint subsets A1, for example, or A of I, you could say. Subsets A of I called partitions or subdivisions of X. Called partitions or subdivisions of X, satisfying number one, all elements of A of I are related to each other. All elements of A of I are related to each other. For all I. And number two, he said that no element of A of J is related to any element of A of I. No elements of A of I is related to any element of A of J, basically I not equal to J. And also the union of number three, the union of A of J is equal to X. That basically means that A of 1 basically union with A of 2, union with A of 3, union with all the way up to union A of n is equal to X. And of course, A of I intersection with A of J is equal to the null set I not equal to J. And these subsets A of I, and these different subsets A of I that we talked about here, the subsets A of I are called equivalence classes. So that's basically again the same situation going on in this example, right? Now we are done here. So what I want to do now is that basically in the next video we will talk a little bit about exercise 1.1. So I'll see you in the next video, and thank you.